Hello, my name is Gabriel Leal. I'm a student of mechatronics engineering, and I'm the head of the mechanics department for the submarine.
Hello, my name is Maritza. I studied mechatronics engineering, and I worked on the mechanical design of the submarine.
Hello, my name is Javier. I studied robotics, and I worked on the electrical design of the submarine.
Hi, my name is Jair Barrera. I study mechanical engineering and I work on the mechanical design and analysis of the submarine.
Hello, my name is Diego Martinez. I study mechanical engineering and I worked on the mechanical design and analysis of the submarine.
Hi, my name is Jorge Vasquez and I am studying mechatronic engineering. I work in the mechanical design of the submarine.
Hello, my name is Marcelo and I studied robotics and I worked on the circuit design for the submarine.
Hi, my name is Sebastian and I work on the development of the gazebo simulation environment and in the mission algorithms.
Hi, my name is Andres. I study mechatronics engineering and I am the current captain of the RoboSub team. As the pandemic continued to be a health concern, the design presented in RoboSub 2020 was not manufactured. Thus, the team focused on identifying areas of opportunities for improvements in the design for future iterations, which will be addressed in the next section. Thanks to these efforts, brilliant advantages were achieved regarding stability and modularity.
The submarine design has 3 ribs supported by 4 horizontal and 4 vertical supports within the bottom of the frame. 3 pressure racks with all the electronic components are held up to maintain the center of mass stable. Furthermore, it has 6 thrusters to achieve movement in 4 degrees of freedom, and on top of the submarine, a buoyancy foam is added to balance the flotation of the submarine. Finally, the torpedo launcher, the marker dropper, and a robotic arm are also included for some of the challenges.
The selection of the materials was a fundamental part of the process design. After a careful analysis, we selected Nylamide for the frame, as it is lightweight and has low corrosion rates, ideal for the conditions that the underwater vehicle will undertake. Up to 80% of the new design is composed by this material.
As for the electronic system, a new PCB design was made, building on what was done for last year's submarine and on our previous RoboBoot entry. We decided on creating a new PCB design which could be used for UUV and USB.
The primary enclosure inside the UUV houses the majority of the electronic system. This enclosure holds a new PCB design in charge of handling power distribution and motor control, replacing 2 PCBs that were used in the previous iteration. Also, 2 secondary enclosures are used to store LiPo batteries, one battery providing power to the motors and the other to the Jetson and its peripherals.
As stated before, the VTEC U3 vehicle presented last year was redesigned considering stability, manufacturability, and modularity as the most important design objectives for the current iteration. Nevertheless, a number of features are maintained as were deemed appropriate.
The general slot shape of the vehicle was maintained, given it has been proven to be efficient backbone for the structure in the last competition. The thruster configuration is also maintained, as it provides enough maneuverability to navigate through the different challenges.
The stability of the submarine is of great importance since the thruster configuration is not able to provide actuation in pitch. By adding a buoyancy foam at the top of the submarine and by displacing heavy materials at the bottom, the center of mass and the center of buoyancy will be separated, which is essential to ensure passive stability for roll and pitch without the need of actuation.
Another major change in the frame design comes in the ribs. While the first iteration of the rib was made up of 4 parts, the final iteration is one single piece, which brings durability, major resistance, faster construction time, and easier manufacturability. The selection of material and method of manufacturing allow us to complete all of this.
Another important feature of this design is its modularity, as the parts can be changed easily without the need to disassemble the whole vehicle. For this purpose, Bosch aluminum profiles were selected to support the frame structure and to allow the placement of different components.
The grouper design changed compared to the last year's design. The type of the grip of this version is linear along for better control thanks to the robustness of the design.
The torpedo launching system was also redesigned. The change came in the selection of spring-loaded torpedoes, which free the energy demand and programming requirements. in comparison from the linear actuators of the last design. The current design allows for simultaneous shooting of the torpedoes using just one motor.
The marker dropper was redesigned as it now uses a crank slider mechanism to release the markers into the objectives. This new mechanism converts a 90-degree rotational motion of the servo motor into a linear movement.
The electronic design was of major importance. It paid attention to aspects such as board size and signal management, both of which were taken into account at the moment of layout drawing and track routing. Some key improvements, which, with respect to the past version of the board, are the individual fuses and current sensors for each of the thrusters.
The manufacture of the VTEC U3 was set to be done during February. However, due to contingency regulations, we couldn't manufacture the submarine as all laboratories were closed. Hence, the focus shifted to further understanding the system behavior through several analyses and simulations utilizing SolidWorks tools. Also, the electronics development was performed up to a theoretical proposal, as no physical development was possible.
The SolidWorks static analysis was used to the analysis behavior of the material when subjected the static loads to observe the behavior of the rib design, where it is in compression or tension. For the simulation of static loads, the analysis of the different types of the dynamic was carried out in order to observe the behavior of the stress subjected in the rib according to the loads that will be used in the submarine. It was observed that the annealement material supports the loads that will be subjected the best.
The SolidWorks CFD tool was used to simulate the movement of the sub through the water, such as translations and rotations. These simulations are important because we are able to analyze the effect of the geometry of the submarine on the drag. With the flow analysis, it was determined that the most of the velocity lost was due to the central support beam and the battery racks. To solve this problem, the surface area of the support beam was reduced, and the domes for the battery racks were added. Thus, the final drag of the UUV was deemed low enough for an appropriate performance on the competition.
Finally, the new electronics design is safer and more reliable. Now, each motor controller has its own fuse and current meter, which can be used to predict and prevent catastrophic failures. Furthermore, data from the current meters can be used to perform preventative maintenance. For example, if a current consumption higher than the nominal value is measured, the motor can be inspected for wear.